So we have submitted some dates to the park rangers for next year. Unfortunately, we cannot return to the mountain for the rest of the year, but we already have dates for January submitted. We expect the rangers to approve them unless they want to wait until later in the year to make sure that conditions are okay. But we're optimistic that by January we can resume members only start parties. The plan is to have only members on the mountain with no visitors and no guests. Typically members only, they keep to themselves with their own telescope. They may invite others to look through, or if they have photography, they might invite them over to the computer to look at the photos, but they don't have a long line of people there. They don't have to worry about people touching the telescope. So if everybody has a mask, you can come up to somebody else's telescope and it'll be relatively safe. So members only is what we're planning to do. We also will have some new guidelines to follow. And unfortunately, we will have to require a waiver to make sure that everybody's aware of the safety conditions and is responsible for them. And that paperwork needs to be signed before you go to the mountain. So we will have some electronic signing of the document so that when you show up, you show us your receipt. Mm-hmm. And that gives you a spot. So we will be turning away people that show up, even if they're members, people that show up without the paperwork.
So and where does one get the paperwork?
We will send out the paperwork over email, and then you can have it signed online. Mm-hmm. And then you bring your receipt.
Have you talked to the Randall Museum with regard to whether they're having meetings there anymore at all, or what their status?
I've checked over the last few months, and maybe a couple of times. I haven't heard anything positive. They don't even have the summer camp that they typically have with elementary school kids.
When this all started, the Randall Museum was like a designated sort of a daycare type of center for city workers, police and firemen and so forth. So I think that they had sort of set the facility up for that. And maybe because of that, they can't host any other events, although they are having people in technically. So I don't know the latest, but I remember that was what they were doing.
Yeah, they don't have any dates yet until, and then with the city schools being closed, I'm pretty sure they'll all be swamped once school opens again with activities.
Yeah. For those members only star parties that PJ was talking about, does anybody have any objection to doing that? We know that everybody wants to get back up on the mountain, and we know that we want everyone to be safe. So, the protocols that we're starting to draft up that we have to review with the rangers are about having people do a waiver, about people doing a signature when they do get up there. So if we ever had to go back and trace because of an infection who was there, we'd have that. Masks will be required, no sharing of telescopes. Cars have to be, 6 to 10 feet apart. It's kind of the same protocols that we're seeing everywhere, but does anybody have any objection to those? Because we're still thinking it through, and we want to, if there's something we've overlooked or a consideration that we could add in, we'd be happy to do that, where possible.
I don't know.
Always good to pulse the first group, so. And to let you all know we're working through that as much as we can. So we'll be ready to hit the ground.
Mm-hmm. Yeah, I want the Randall to know that we'd like to have our regular schedule before the beginning of next year, even if we can't go quite in January or February.
Have you reached out to Nathan? Is he responding?
I haven't talked to him lately. I wondered if a representative might, or a representative group might be going to the city of San Francisco and asking about our location. If it were a normal year, you'd be speaking to us, Simon, in a lovely auditorium and a city-owned property that would be with a beautiful view of the East Bay in San Francisco, and we would have taken you to dinner before you started talking. And I'm sorry that we didn't get to do that.
Well, that's the situation right now. So
I know.
Simon, that's your cue to ask for a rain check for dinner.
Yeah, hopefully, well, at one point this thing will change. Hopefully sooner than later.
I know. Should I introduce the next two speakers and then Simon, or wait another 5 minutes?
Couple of minutes.
Okay.
Did anyone see the sliver of moon, I guess 2 days ago, with Venus right next to it? I guess 2 mornings ago, 3 mornings maybe. It was gorgeous.
No, I didn't. In the morning?
Yeah, it was in the morning. It was, there was a remarkable amount of light in the sky. I was surprised that I could still see Venus, but it was gorgeous.
Mm.
I saw the moon setting 3 or 4 nights ago. It was very nearly full, and it was already maybe 3/4 of the way in below the horizon. It's been so odd with the weather. So we had only a couple of days of sunshine over the weekend, and then it flipped back to cloudy and chilly until a day or two ago when it was hot but muggy.
We'd be happy for cloudy and chilly right now.
Linda, you can start your introduction now.
Okay, I will do that. On September the 16th, we're having a lecture called The Formation and Evolution of Binary Stars. Binary stars are one of my favorite things to observe in a telescope. It's by Aaron T. Lee. He's the professor of astronomy and physics at St. Mary's College of California. Nearly 50% of the stars we see are part of a binary system. Double stars and multiplicity of stars are a common phenomena in the Milky Way. Our speaker will discuss the process and how observations using some of the most powerful supercomputers in the world of stars and galaxies rely on our understanding of this stellar binarity. That's September. And then October, we will begin our lecture a half hour earlier because Bob Noya, who lives in Hershey, Pennsylvania, will be speaking to us. Many of you know him from past years when he was with us as a member. Finding Life on Other Worlds. He's an award-winning science writer, and he was the editor-in-chief of Sky and Telescope magazine for several years. Are we alone, or do we share our solar system and galaxy with other life forms? Right now, we don't have the answers to these profound questions, but scientists are in hot pursuit. The technology of searching for life on other worlds has received a level of maturity where the first definitive evidence could come in the very near future. And Bob Noya is looking forward to seeing a number of us on the Zoom screen when he talks on October the 21st at 7:30. Tonight's speaker, Simon Birrer, received his degrees in physics from the Swiss Federal Institute of Technology in Zurich, culminating in his PhD in 2016. He's a postdoctoral fellow at Stanford University since the fall of 2019. Before joining Stanford, he was a postdoc researcher at UCLA, Department of Physics and Astronomy. Throughout his career, he enjoys interacting with the public, giving lectures, telescope tours, planetarium shows, and he hopes to engage and promote the talents and curiosity of the next generation of physicists. Tonight, probing the fundamental physics with strong gravitational lensing is his topic. Many useful results for cosmology have come from this phenomena. Dr. Birrer will shed more light on how astronomers are utilizing strong gravitational lensing to probe the nature of dark matter and dark energy, the dominant yet unknown components of our universe. And we look forward to your lecture right now. Thank you, Simon Birrer, for being with us tonight.
Thank you very much. So I'm gonna share the screen, my screen. And please interrupt me anytime so that we can make it as interactive and as convenient as possible during these times. So it's my great pleasure to be with you here on the web, so to speak, talking. The title of the talk is Probing Fundamental Physics with Strong Gravitational Lensing. My aim is to give you a bit an overview of how the field of gravitational lensing has evolved, and with it, its thinking over the last about 100 years. And what questions we can address with utilizing this phenomena during recent years. And this is the field that I'm working on myself. So some recent work or press releases I participated, and I'm happy to get questions of any sorts by you. Before diving into the gravitational lensing picture, I take a bit of step back and first give another picture here of this talk will be about phenomena that are not so related with our daily life, or not at all related with our daily life. And so we have our prejudice of what we think is going on, or the way we can very well explain what makes sense for us on Earth. And maybe even here on this Zoom call, we may have people that are a bit tilted relative to others. And that's not what we daily life experiences, but we know the Earth is round, a sphere. And so taking a bit of step back of that, maybe things may be a bit different than what we imagine. And one step further, and this is my favorite picture that's been ever made. This is a long time ago, way before my time, of the first moon landing, the picture of our Earth from the moon. So this is as far as humans have traveled themselves to look back and reflect on our little place on Earth. So to start with gravitational lensing, this is tightly coupled with the history of general relativity itself. And so I'm gonna talk first, as you may know from history, Einstein proposed general relativity in 1915. This is 10 years after the theory of special relativity that was known by Einstein when he effectively wrote it down, that there was something not right by describing the dynamics of gravity with special relativity. And in 1915, finally proposed a metric theory to do it. And at that time, the primary reaction to this work was effectively this. This is crazy. It's effectively not part of the daily life experience of even the most known physicists, so to speak. So at that time, this was very new, very unusual, and by most people, eventually not well received. There were a few people that either understood it or at least believed that Einstein must be a smart guy, and so I take it serious. And there were some people dedicated that took it enough serious to went ahead and ask, how can we test this theory? How can we see something that may give us hints whether this can be right or wrong. And this lets and Einstein himself proposed effectively at the same year when he wrote this theory down, is his expectation is that there is such a phenomena as lensing, that light will not travel on straight lines, but will be curved. And this was effectively the first test of general relativity. And this leads me to the Eddington experiment. So here, this is a very a sketch of when you have a star on the sky or its apparent location. That's where we see it, but where it actually is down here. And when the path of the photons, the light, comes close, in that case of our sun, it gets bent around by the gravity of gravitational potential, or the curvature induced by this matter, to effectively bend the light such that when we look back, we see it up here rather than at its original position. So now that was written down, and we know how much this deflection angle is, so this change when the sun is in front. There's just a problem with it, is that this difference in angle on the sky of order an arc second is so small, and the sun so bright, that anything close to the sun is basically outshined by the sun. But luckily, there's a rare occasion of a solar eclipse. And that the next one after 1915 that happened, that people actually could go to and watch it, was the one of 1919. Actually, there was one before, but they failed the experiments because of bad weather. And so the first one where they could take picture was in 1919. And so what the Eddington and its team did, was actually effectively described in this picture. They measured the position of the stars when the sun and the moon were in front. And half a year later, or even a few months later, you can watch the same position when the sun is not over there and it's night sky, and you see the difference between the distances of these stars. And so you can measure the induced lensing effect, so to speak. And this was the first test of general relativity. And this was really, in that sense, a breakthrough of that the prediction that Einstein made then was right within the uncertainty. And the prediction that was thought to be the correct one by, at that time, probably still the majority of renowned physicists, was not according to what the data give. And so it was really that experiment of gravitational lensing that changed the view of the community, or most of it, to take it serious. So in that sense, gravitational lensing is really tightly coupled to the general relativity and its progress and its success eventually. So this lensing effect that I showed here is rather tiny, so very tiny deflections. But even at that time, Gedanken experiments, or in the mind's thoughts, one could draw some other sketches like this one here. What if this effect happened to be very strong? And by strong here, it means the star is here. Oops, going back. And there's this massive foreground object, which effectively acts as a lens. And it bends light that we not only see a shift of this object, but actually a multiple appearance of it. And in that case, we call it strong gravitational lensing. This was formally known that this is theoretically possible in the 1920s. Einstein themselves at that time thought, like, this is never going to be seen, because we don't see any objects that can be such massive and distances so large that this not really bothered about whether this is a real phenomena, or you can just write it down on paper and do the math, and it's nice. And time went on. More and more was known of the universe. it was known it's much larger than we thought. It's expanding. There are actually galaxies outside of our Milky Way that are much more massive than our own. And a lot of knowledge has been acquired such that this phenomena was not anymore just a theoretical concept, but that was something that people were actively looking for and searching. And in 1979, when there were photometric plates, no CCD detectors, this image was made here. And what it showed is a so-called twin quasar. A quasar is supermassive. Now we know what it is. At that time, people didn't really know what it is. But what we know now, it's a supermassive black hole that has millions of solar masses in mass that is sitting in a disk of hot gas that gets accreted onto the supermassive black hole, and this accretion emits a lot of light and energy. And this light that has been emitted effectively outshines the entire galaxy that where this supermassive black hole is in there. And that is now known as a quasar. So it is a very bright source that outshines a galaxy. And what it's been seen here is that these two blobs have effectively the same spectra. So it is indistinguishable in any regards. They're just very close to each other. And once deep photometry also showed that there is a blob in the middle of it. And this blob in the middle is another galaxy in its foreground. And so that was the first discovery of an object that has been lensed and seen twice. Nowadays, with, for example, the Hubble Space Telescope, we can zoom in. We have way better facilities to do observations. And this is effectively the zoom-in version of it. So we have the two quasars and the galaxy sitting here in between, more close to one of those quasar. And so this galaxy is the lens. It's not a single star. It's an entire mass of the galaxy that is the lens. So this was in 1979. Here, this jump is all more than 20 years, 25 years about a step. And so gravitational lensing, as I said, is predicted and produced by, well, the theory of gravity that we have, that matter bends space-time around it. But we have analogs to this in our own, on Earth. So one analog to gravitational lensing are my glasses themselves here. They also change the path that light travels, and in a way that they focus that I see a bit more clear. There are other phenomena we can observe where light is bent, and I show you this movie here, where we even see multiple appearances of a fish. And this has to do with that effectively the light travels differently, or the speed of light is changed when it goes into water, and this deflects the light rays. And something very similar happens on cosmological scale with gravitational lensing, that we know that when we go into a gravitational potential, the clocks are ticking slower. And if you look from outside, effectively you see a difference in the speed of light, even though locally you measure exactly a constant. So in that sense, you can we can replace the gravitational lensing phenomena with an optical lensing phenomena. So all the language that we use to describe this phenomena is in pure optical terms. And that's the language that, and then we can translate it into, okay, this is now matter and not just a diffraction index or some piece of glass that does the lensing. And nowadays, we see this phenomena appearing in the numbers of 1,000 and ever increasing. And this is mainly thanks to the Hubble Space Telescope. Show you the first image. So once Hubble turned on pointing on a sky, it is a very high chance that one or multiple objects in this image has actually lens components in it and distortions. And when we are more clever and look and searching for these objects that are still rare on the sky, montages such as this appeared. So here you see a collection of what we call galaxy lenses, which means that a galaxy is the lens, the matter that bends light. In that case, these are massive elliptical galaxies. These are the ones that you see in yellow or red color. And the galaxy behind that is at higher redshift earlier in the universe is the blue part. These specific objects were selected such that in a spectra that was pointed on the elliptical galaxies, there was recognized that there is a spectra at higher redshift. And then Hubble turned on and it confirmed that when it's so close to another massive object in front, it has to be bent. And these phenomena exist. Here, one movie that illustrates the phenomena of how light rays travel through the universe gets bent around a massive galaxy. And then when we look at it in projection, we see this phenomena. And this is known as Einstein rings, when they're perfectly spherical. And if it's a bit asymmetric, which real life is, you get various different components. Mainly we divide between what we call a double and a quad lens. Double mean when we see, for example, as here, two components appearing. So there's one blob and another blob. Or a quad, where, let me see whether I see one. This effectively is an Einstein ring, where effectively a specific component is imaged here, 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 and here. So 4 times it appears. We'll come to that. And the phenomenon not only exists for a single galaxy that warps space-time around it, and in the rare occasion that a source is right behind it, creates a lens. The largest, most massive objects in our universe are galaxy clusters, so an assembly of hundreds or even thousands of galaxies present. And when we make very sharp images of these galaxy clusters, these images look like this. Basically, yeah, this is one of my favorite images. This is also the one that my title slide is on, where you see the richness of this phenomena. So the lens in that sense is not a single galaxy, but all these yellow dots are effectively members of this massive structure. And these very thin stripes here that you see are highly distorted, highly magnified along one axis, effectively small little galaxies sitting way in the background. And so this galaxy cluster here serves as, we call it magnifying glass, that we see very small scales that we otherwise do not have access to. And we see also that this part here is also this guy here. And now you can do, okay, can you see the counter image of a certain blob? And this is active research to find as many counter images of certain lens sources, because those give us a lot of information of what's happening in this cluster and along the entire line of sight, effectively most of the history of the universe, of how it's being expanded and what its structure is. In particular, when looking at this image, what we can learn from this phenomena is effectively the matter that is bending the light. So we know how much matter there is in this cluster from this phenomena. And now when we study these galaxies, which have a lot of mass, we miss about 90% or even more of the mass to cause this phenomena of this highly magnified arc. So within that aperture here that I highlight with my cursor, there is way more mass than we think is basically we call it baryonic, or is made of the stars that we see, or even the gas that we don't see. And that's what we call dark matter. And one way to use this phenomenon is learning about what is this dark component of the universe. And so when staring on clusters like this, from time to time, we see phenomena like supernovae explode. These are rare, but if you're patient and you watch on clusters, you may see one. And this is illustrated here. So this is another cluster where you see an elliptical galaxy with spiral arms. So these are star-forming regions, probably very similar than our Milky Way, so to speak. And one image of this galaxy is here, another one is here, another one is up here. And this spiral arm, one of those, gets effectively lensed and warped around of another galaxy that is a member of this cluster that forms the lens. And there was an image taken that showed these 4 blobs, S1, S2, S3, and S4. And these are images of the same supernova that exploded in this galaxy that is being lensed. And now comes another phenomenon, namely that the time it takes for the photons, for light to travel through this lens differs from one image to the other. And so this is illustrated in the next slide. I come to time travel soon. So there's a path difference between these 4 images. This path difference between these 4 images is rather small, such that we expect the differences between when we would have looked at this galaxy very sharply. The supernova went off maybe a few days before at that image than on the other one. But when we zoom out on the cluster, when we look at the other images, the light travel path substantially differs. And light has a finite speed. It's the speed of light. And so if there's a different light travel time or path, we have a time difference. And so there is a gravitational lensing time delay. And so when we have, from our models of our understanding of the cluster mass, we have a we have an expectation of what that time difference is. And it turns out that this image here, right in the middle, this guy here, we expect the photons emitted at the same time when this supernova went off to arrive later. This may look here a bit counterintuitive because this path is presumably the shortest one relative to the other one. But there is another optical phenomena of a time dilatation when you go through a gravitational potential, and that counteracts. So actually the speed of light is changed when you go through the center. And so when we saw, or the team saw the supernova, we had the following expectation. This one was the one that was first observed by Hubble. And the expectation was that there is a supernova will be seen 1 to 5 years later in this galaxy, which is the same galaxy, but we just see a bit of different past of it. This guy we missed by about 50 years earlier, and this by about a decade or so. So these are in the past, so hard to predict. But when the team saw this pair of supernovae, it proposed that Hubble continuously, or on the level of every 2 weeks, is pointing at the cluster to see, will it change? Will we see a supernova here? So effective, and indeed, and this is effectively the raw images of Hubble in certain sequences here in January 2011. That was before the time that even we saw that supernova here. This is April 2015. This is when Hubble detected these 4 blobs, and everyone was like, whoa, what's going on? And then the prediction was made for where this blob will reappear. And, or behold, there was indeed a déjà vu that there was a change here in brightness discovered a few months later, while Hubble was continuing looking at it. And so this is a déjà vu. And so, and now this phenomena of time dilatation itself is a nice illustration of the effect, a nice confirmation of the effect. But we can use it actually to learn even more about the universe than just predicting when a supernova will reappear in another image. In particular, what we can learn from the time delays is actually the size of the universe. So going back to this picture here, this size is not in scale, so that the difference length between the source and Hubble is way larger, and so the angles are way shorter. And what we would like to know is how large the universe is, or how far away is this galaxy here. And that's one of the hardest observations we can do. Either we know intrinsically how bright or how big this object is, and so we can do trigonometry, but that's not something we have access to. But when we know the time delay difference between two images, we can learn about the total path length from looking at the angles that we see in between. And so we can turn that exercise around and not just saying, can we predict when an image appears? We can turn it around and say, when we measure when the images appear, we can actually predict or determine the size of the universe or the size to these objects in the background. And that eventually tells us how old the universe is, and we can translate it in how fast the universe is effectively expanding today. And that comes to switch a bit gears to the science and the novelties and the excitement that we have nowadays in our community. And some of it is reflected or enhanced or through the media. Here, there's some outlets. This was from last year. There's many more articles. Some of you, well, before I go in it, are there any questions that you have on the story or the phenomena? Just want to stop for a moment. If not,
could you go into the gravitational potential and time dilatation, how that works a little more?
Yes. So so what effectively happens is if we are sitting on Earth, our clocks are ticking slightly slower than if we are in orbit above the Earth. So for example, GPS needs the clocks to tick a bit differently. So this has to do with that the gravitational potential makes our clocks tick a bit slower. And what this then has the effect is that when we are outside of Earth and we look down at Earth and see how fast light is traveling, we actually see that the light speed is smaller than the speed of light that we expect, because the clocks there, we see them ticking not as frequent as where we are sitting. And the same or even more dramatic effect happens in this massive cluster. And so when the photon travels here through the center, that when observed from outside effectively has a different speed of light. It's not that locally you measure a different speed of light. You measure exactly the same speed of light, but that has to do that your clocks are ticking slower. And so that is effectively the phenomenon that gives rise that the central one is always the last one to appear. So it's the slowest.
Thank you.
Yeah. Welcome.
Do we know that it is the same supernova for sure on this?
Very good question. So when I go here, when we see all these spiral features and we can localize where the supernovae appear. And so what we know, we can reconstruct, I didn't show it here, but when we do the delensing, so to speak, we can get the same intrinsic morphology of the spiral galaxy out of that image. When we know the phenomenon, we can redo the lensing effect. And so we can localize the position of where this supernova is. And then we can translate it to another image that we see, and we see it at the same position where we expect it to be. So this gives a very good prior of that it's actually the same. That's one. The other is we can get the light curve of the supernova. So a supernova is not just a flash and then it's silent. It's a month scale duration explosion by effectively an expanding plasma or shock wave that expands in shells that lasts for longer. And it also changed the color. So it depends on what kind of radioactive decays happen during the explosion and the time scale. And so we see a brightness change and also a color change of the supernovae. And each supernova is individually different. So it depends on the mass of the star, what its composition is, and even certain things we don't really understand. And when we now look at the supernovae that went off, we see effectively the identical light curves going up and down in the different colors. And so you have to go against many odds to say it's a different supernova that went off that looks identical in time, in color. And for this one, the team even was able to get a spectra where it actually sees the emission lines of the radioactive decays of the material. And that's effectively how we really confirm that it's a lens. So the different levels when we say it's a candidate lens, and it's even now when I'm talking with my colleagues, sometimes there is ambiguity. And so do we call it a confirmed lens, a candidate lens? What do we need to confirm? If we normally point Hubble on it and we see clearly the lens feature signature and we can make a model of how the bending actually happens and we can reconstruct the source, then we call it a lens. Some people say, it's fine, I believe it, but I wouldn't really solidly call it a lens unless I get spectroscopic observation, where I really see that different components are identical in how the spectral lines are emitted from it. And then you have to run against many odds.
Thank you.
Yeah. So going to the Hubble constant tension, or some articles here writes, these are articles from July 2019 and so what this here illustrates is that the community, which I'm part of, is not really sure, or there's a debate between different measurements about how old the universe is and how fast the universe currently is expanding. And so, yeah, is it a statistical fluke, or is there some new things that is lingering mystery, so that we have to change and revise our model of the universe? Wouldn't be the first time, will definitely not be the last time. And the debate is going on for definitely a couple of years when measurements became increasingly precise, but they became increasingly not agreeing with each other. And one of these press articles here in January 2019 was featuring a quasar with a double imaged gravitational lens could help finally figure out how fast the universe is expanding. So that's the title by the journalist. And what is featured is a gravitational lens, similar than the ones that you saw. Here it's a quasar, accreting supermassive black hole. And similar to a supernova, it's not really exploding a quasar, but it's fluctuating. So sometimes the accretion state is such that it emits a bit more radiation or luminosity light, and sometimes a bit less, so it's flickering on the sky. And this flickering can be used to measure the relative delay between this quasar image and this one here. And so we can use that then to measure distances and the Hubble constant. And here another press article, October 2019, that's where we use it. These are different lenses here. You see a bit a slightly different image. What we're using here is not the Hubble Space Telescope, but adaptive optics instruments on Keck on Mauna Kea. So Keck telescope is a 10-meter primary mirror telescope on Mauna Kea, and in the infrared, adaptive optics can effectively correct most or a lot of the atmospheric blurring that we all face when we do our observations. And correcting for those, it can create remarkably sharp images. And for those, we have also measured the time delays. And the Hubble constant, so that is here in the press, that's not, it's something really imprinted in the universe, and it first started with Edwin Hubble and Georges Lemaitre. So nowadays the international community recommends calling it Hubble Lemaitre constant to have not just one person the credit. And so this is the diagram that made Edwin Hubble famous. And what it shows, as you may or may not know, please interrupt me, it shows that different galaxies that are further away, so this is distance in units of parsecs, and here this is velocity, that objects that are further away from us are moving faster away from us, with some scatter, but it's effectively a straight line, which is known as the Hubble Law. And the steepness of it is the Hubble constant. So how fast is an object moving away from us when it's 10 to the 6 is 1 megaparsec. And you may look at this picture and say like, okay, this means that the universe is steadily expanding and things that are further away of us are actually faster expanding. And the picture you can have, or at least paint, or an artist did, it's not really the true picture, is that effectively the entire scales of the universe are expanding. And this is then known as the cosmological redshift when you really look back in the past, that effectively the entire scales, and with it, the way the light is propagating, and as they propagate, or their wave behavior, the entire wavelength effectively stretched. And so this is then the redshift, which is the stretching from smaller wavelength to larger wavelength. And so this is a strange picture, also really debated in the early days of 1929, not as much debated than the general theory of relativity, because it wasn't really unexpected, and that Einstein was right again. So this is can be fully explained with general relativity. It's unintuitive, but at least within general relativity, there's a clear framework to describe that expectation. But often when the community then looks in more detail on the universe, there are an entire journey of unexpected observations. And one of those, it's a bit illustrated here in these plots, where these were made in the late 1990s, where it's not a straight line how this expansion happened with distance, but there is a curvature, a curvature in there in the plot. And this is known as cosmic acceleration, so that we are not only things that are further away from us move further, faster and faster away, so to speak, or at least the space is moving. It's not really the objects that are physically moving. But this entire process is, with recent cosmic time, accelerating. So we're moving faster and faster away from each other. Unexpected for most, and led to the discovery of what we now call dark energy. We don't really know what it is, but we can put it into these equations and they will describe the data remarkably well. And that's effectively illustrated here. One Einstein, well, he was not alive when these discoveries was made, but he would have said, works for me too. He had not really, he was not in favor of such a behavior, let's put it that way. But within the theory that he developed, it can account for it. And what you see here is then this Hubble diagram, so we call, which describes how distances and the cosmological redshift evolves in the measurement, and the black line is a model that we have that describes this data set. So what this diagram here does not do, or what it does, it calls it distance modulus. What it doesn't do is actually write absolute distances to this object, because these are very hard. Relative distances are, I wouldn't say super easy, but much easier. If we have a supernova going off twice as bright, or 4 times as bright as another one, we know it's twice as close to us, even though we don't know its intrinsic brightness. And where we're currently at are, and that's effectively illustrated in this plot, where this is August 2019. I'll show you a next figure where it's a bit updated. This is 1929. And what you see when you compare the numbers here in terms of kilometers per second per megaparsec, so per megaparsec, this is this line here. Edwin Hubble was, when we have here a number around 70, he quoted a number around 500. So he was way off. So there were a lot of measurement errors by a factor of almost 10 off in terms of the calibration. In particular, these objects just happened to be much more distant than what he thought. So the trend he got, but the numbers he was awfully off. And nowadays we are much more precise, and there's a wealth of different techniques to describe or measure scales in the universe to effectively infer how fast it really physically is expanding. And what is illustrated here is many different data points that all somehow, with uncertainties, point to a value around 74. While there are other measurements that rely on what I call sound horizon physics. You can already forget it, that rely on physical calibrators that happen in the very early universe, how the cosmic microwave background has been emitted, the scales that are imprinted there, and they point out to a lower number by about 8%. You can think it's like tiny, but if you sum up the different independent measurements, you get something what we call around 5 sigma, where 5 sigma is a statistically very, very unlikely scenario that they can occur if both measurements are correct. And when both measurements are correct, then this means that something in our understanding of the universe is not correct. And so that is the debate that's ranging around what is known as the Hubble constant tension. And since then, August 2019, there are many more press articles. So the New York Times features it. And what I already told is like, okay, what we need now is independent measurements of that Hubble constant. We tend to, if you put a lot of weight on a single measurement, to effectively throw over, to a certain degree, our current understanding of the universe. People may not believe it. And what people want and scientists want are independent confirmation of it. And so here we're looking really for different measurements that can give us the same to see whether actually there is some hint of new physics or not. And this is then time delay cosmography. I've already introduced it, that we can turn around the measurement time delay to a predicted expansion rate. That's the game. And the way we do it here, and this is that is back there, the slides that are shown, is with quasars that flicker. And what we do here is we use about 2-meter class telescopes on sites in Chile, or in remarkable good sites, and we measure every night the brightness of the individual quasars. And what we can get is a light curve, and we get the flickering with some time dilation. And when we then put the data over, here's another quasar. Here these are blended and ground-based. And we have here the remarkable data, how the brightness evolves from the different images. And you may see already by eye, what is the time difference between images A and B. And you can shift by eye the curves to see that this rise here occurred here a bit earlier. And so we can measure the time delays. And I'm involved in this business since about 5 years, and I'm actively developing techniques to do the analysis. And the latest results we have that I had the chance to lead in this collaboration effectively made some changes. That our new measurement, before it was up here, this green, moved back down. And so there may be less hints of attention with these measurements that are super precise. And so effectively here, the story for me this last year was not that we always move forward more precise, that things stick what we had, but that we had to revise certain assumptions that we made. They lead to larger errors and move the measurement. It's a very, it's a tricky measurement that we're doing. And we really want to be 100% sure that the measurements we have really corresponds to the errors that are there statistically. And in that case, this measurement, to some disappointment, was not in that sense excitement for new physics for now. But that is the life of someone that wants to push the edge, and sometimes you have drawbacks, or you revise a statement and see how the community as large can learn from it. And here another 8 press release of something else that I want to mention in the last minutes that I'm also involved in is in dark matter. And so this is the same poly-lensed quasars that we have for the Hubble constant measurements that we use to learn about the small scale structure of the universe. And what do we mean by that? So this is a artist illustration part, or at least this galaxy, and the thing around is a simulation of what we think dark matter may be. And this is expected or predicted that there are a lot of clumps, we call them substructure, are surrounding our Milky Way and any other galaxy that are not visible, or the large fraction of it is not visible. The good thing is gravitational lensing doesn't care whether there's stars in there, whether there's gas glowing. It just bends light when there is matter, no matter what type of matter, and thus is very sensitive and or has a window, so to speak, into the very dark universe where we don't know much about it. And so the idea here is effectively learning from the distortions of the lensing feature of whether we're living in a universe that is more looking like the top panel or the bottom panel. And that is a hot debate currently of what dark matter is. We don't know it. It's a placeholder. We have very good numerical simulations that allow us to make prediction, and a lot of them are in agreement with what we see. And one of those predictions that was made is that there are a lot of clumps, that some of them, the larger ones, host galaxies. And indeed, we see now these ultra faint dwarf galaxies around our Milky Way. So here there are 2 of those presented here. And they can exist in different scenarios of what dark matter is. One is a bit cuspier and one is a bit smoother here. But lensing, when light travels through, can distinguish, and that's what we are now actively working on, to see whether they're really truly dark clumps that don't have a galaxy sitting in there. And we want to really know and prove or disprove their existence through our observation. And that leads to insights, or we can at least say what dark matter is not. And that's a step in that direction. And recently we have accumulated a lot of data here. This is just, in that sense, I'm working in a field that has a lot of pretty pictures. So what we see here is 12 of these quadrupole lensed quasars. They all look a bit different, different colors, different host galaxies. And what you see on the right is a model. And this model was generated with a lens model that we have and a computer simulation, so to speak, that describes the entire physics about how this distortion works. And so we can go to the, effectively to the pixel level of Hubble Space Telescope observation to reconstruct the different light paths in the computer. And that's what I'm actively working on, to get effectively these lens models out of it. And the last slide I have is another phenomena of gravitational lensing that I like to show, and you probably have all seen. And this is this one. The first, you may not have seen it with a title of a gravitational lens, but what you see here is the highest resolution image that has ever been made by humans. And in the center here, there is a massive black hole, a supermassive black hole. And this image is made by the Event Horizon Telescope. And the emission here is in radio. And they did a remarkable job of effectively creating an image around its close vicinity of a supermassive black hole. And when I first saw it, I was like, yes, this is a black hole, remarkable, but it's also a strong gravitational lens. So what you see here is not the event horizon. What you see here is structure just behind that supermassive black hole that gets warped around it, and you see it as a ring. So when you see, and this is then the full press here, this is from the New York Times. I think you can take any newspaper. It was so widespread, rightfully. And so I do some slide Photoshop here, first image of a black hole. I change it, the smallest resolved strong gravitational lens they have image. And so next time you stare at that truly remarkable image, yes, it is a black hole. And yes, it's also a strong gravitational lens that we have. And with this statement, I make another gravitational lens. Thank you.
Yeah.
Thank you.
That's it from my side. Happy to receive any kind of questions.
I have one. Has the modeling resolved to the point where you can image the source of what's being lensed? In other words, a picture like the one you just showed of the black hole. Can you actually get a structure, or something we would recognize as a picture of what it would be if you had the lens that big that was more perfect?
So what is the question, whether we can effectively get sort of like de-lensed pictures of the things that it's being warped around?
Yeah, take out all the distortion that you get.
Yes, that's what we do now on a routinely basis. So I don't have a slide that go into the techniques of it, but we effectively propose hundreds of thousands or even millions of different lensing configuration, ask whether we can find a solution that's something that looks like a galaxy originally, that gets then warped around and we see Einstein ring appearing. And that's how we do the entire inference and modeling procedure. And the techniques we're using there has also a lot of linear inversion parts and deconvolution techniques. They're very similar to image processing deconvolution techniques, with the addition of like having that distortion feature in there that is caused by lensing. Don't have one of, I probably should have one of those slides that demonstrates it.
Can you explain how a gravitational lens ever produces exactly two images? It seems like it should always produce a ring, or at least a distorted ring.
So a ring, it will produce when it's when the lens itself is symmetric, so that the matter is really either a point source for the supermassive black hole, or a very spherical galaxy. And when the source is effectively exactly aligned, so effectively when I try to stare here through the camera, and then the warping is very symmetric around all the axes, and that gives you a perfect Einstein ring. When now the source is slightly offset, so when I am the source, I'm slightly lower, then what happens if we now switch a bit around, that the paths that find solution that reach us will be asymmetric. And so if it's slightly offset in one direction, it will find two parts. And I may go back in the, 1 second, please, in the very rough sketch. Here it is. So here it's perfectly aligned. And so you see it in projection twice. But if that star here would have been slightly offset up here, there would still be paths that go below and above, but the path below would go close to that object, while the path above would probably go rather close to where it is. And so it gets an asymmetric positions. And that's also what you effectively see here in that first quasar lens. But one of the images is very close to the lens itself, while the other is rather further out. And that has so little to do with where actually the quasar intrinsically is relative to the lens galaxy. If the quasar were slightly moved, you will get a more symmetric or even like quadrupole imaged or almost an Einstein ring. Does this at least halfway?
Yeah, thank you.
On
No
so
one
many,
else?
oh, go ahead.
Well, if no one else has a question, I have a second one.
Okay.
I was wondering, this might be a whole different talk, but you touched on dark energy and the Hubble constant and in relation to the end of the universe and the three ways that I'm aware of, the heat, death, entropy way, the big rip, the big crunch, the big freeze. Could you elaborate a little bit on those? And the one that ends with it all fading away and we can't see anything, why do they always leave off our galaxy? They always say only our galaxy will be left. It seems that with enough time, even our galaxy would be expanded by dark energy into oblivion. Am I missing something?
So at one point also our galaxy will not exist, but that's not because directly our galaxy is torn apart. So what dark energy is, or what we think it is, or at least how it acts, is that's a constant negative pressure per defined volume element. And so if our galaxy manages to sit always in the same three-dimensional volume, the pressure on the galaxy to being expanded will not change. And it is very, very, very small. It's only when objects are further away, then you have tremendously more volume, and thus the pressure is there to actually expand it. And so if things can manage to stay physically bound, they will not directly be forced away by dark energy. So,
but isn't there a model where dark energy overcomes all the other forces in the universe and it all becomes ripped
yes,
apart? And that would apply to our galaxy as well.
Yes, but it will apply differently in the sense that at one point, the stars will not shine anymore because they run out of fuel.
Well, of course. Yeah.
And so there's a lot that, and effectively evaporate through thermodynamic processes that just, it loses. You can think of that loses piece by piece on tremendously large timescales. Thermodynamic will say that even our own galaxy, once everything collapses, it's either going to be in a black hole or eventually being thrown out. And then effectively what happens then is things disappear from each other. And this is, in that sense, statistically what's going to happen on super large time scale, but it will be in a finite, so to speak, 10 to 100 billion years.
Yeah, but even the mass evaporates with enough time.
Yes, yes.
Okay.
And even black holes. So that's the last piece. Even if black holes stick together, they eventually will evaporate. That is the Hawking radiation. It's not empirically, we don't know that because it's happening in so small timescales that we cannot measure that. But it's something that we expect from quantum uncertainty on the event horizon, effectively, that certain things just evaporate,
Right.
even tiny bits.
And that's the heat death and entropy
Yes,
death.
that is
And
the.
so it's not the big rip or the big crunch or the big freeze.
Yes. I think currently, if we extrapolate our models that we have, the heat death is the expected scenario.
Thank you.
Yeah. And it leaves actually an interesting part aside, Mark. It's more a philosophical one, that effectively the story of our history of the universe, so to speak. So our past and our future will be finite. Even though the universe is infinite in terms of its scales it has, there's no border anywhere, nor left nor right, is what actually could make our story in terms of what reached us is a finite volume and a finite time. And in the future, when the universe is expanding, where we can tell our story, that where we are in, or what we can interact with and influence, will eventually be finite. Not in terms of time. Time can go on forever, but it just has nothing to write books in, or there's no interactions. Yeah. So the book, the story of our life, even though it's super thick, will be finite.
Hmm.
Yeah.
We do.
Yeah. A bit different than the talk on gravitational lensing. Philosophical deviation. Any other question?
I think we're done.
Yeah, pass it back and stop sharing here.
Are there any other questions? Did you have a question, Mary?
I think it was answered.
Okay.
Course of, oh, yeah, thank you.
Yeah.
And I just want to tell the speaker, thank the speaker for making this complex topic very understandable. It was
Yes.
so interesting.
Thanks.
The visuals were extremely helpful.
Very
I had a great help from NASA departments.
that's what we pay them for, right? Among other things.
Well, we thank you very, very much for your time and your interest. And I'm so glad that this is recorded so that we can go back and correct our notes that we're writing, scribbling here.
Have questions? Me.
Right. Yeah.
And
Lovely.
no more questions?
No.
Okay.
No.
Thank you. Thank you, Simon.
Very much.
Thank you. Yeah.
Thank you.
Thank you very much.
Appreciate it. Yeah.
Bye-bye.
Bye.
Bye.
Bye. Thank you.